Proofs by Contradiction and Contrapositive by Abram Anton Christopher Veronica.
Introduction. Like scientists rely on experiments to prove their claims, mathematicians rely on logic and reason in their proofs. Once a statement has been proved mathematically, the logic is undeniable, and the conjecture becomes a theorem. Methods of proof include direct, indirect, induction, construction, exhaustion, probabilistic, combinatorial, non-constructive, statistical, and computer-assisted. In this presentation, we explore two methods of indirect proof: proof of the contrapositive and proof by contradiction. They are closely related, and they both start by assuming the denial of the conclusion. Next slide. Circa 300 BCE, Euclid proved by contradiction that there are infinitely many primes. Normally, proofs use axioms and the accepted rules of inference, but sometimes also previously proven theorems. As for notation, we use if P, then Q. We will write that as if P, then Q. And not P, we will write as not P. Next slide. If P is true, then Q is true. And then not P, then not Q contradicts. So the opposite of P does not imply Q.
So proof by contradiction is based on proving something by showing the opposite is not possible. Proof by contradiction is an indirect proof that supposes for a claim P implies Q if P implies not Q creates a contradiction, then P implies Q must be true. When you then follow through with calculating this opposite claim, you will have a contradiction, hence the name proof by contradiction. This contradiction then proves your original claim must be correct. So instead of proving that P is Q, then Q is true, we prove that P is true and not Q is true will create a contradiction. So here are the steps. So you write the original statement and indicate that you will use proof by contradiction to prove it. Then you write out the contradiction of the statement that you're trying to prove. And then you attempt to prove the contradictory statement. If the proof is correct, a contradiction will be found and you'll be unable to prove this contradictory statement. So the first example is to prove that there is no smallest number. So if you're trying to prove that there is no smallest number by proof by contradiction, we have to assume the opposite, that there is a smallest number, and let's call it x. Now let's look at the number x minus 1. This number is smaller than x. This causes a very obvious contradiction because x minus 1 is smaller than x, and we said that x was the smallest number, but we have found a smaller number. This proves that there is no smallest number and numbers continue to become smaller to negative infinity. Our second example is proof that root 2 is irrational. So let's assume the opposite, which is root 2 is rational. If it is, it can be written in the form P over Q, a fraction in simplest form, because all rational numbers can be written in this form. So if we say root 2 equals P over Q, then we can reorder this and square both sides and say 2 times Q squared equals P squared. And the left side, Q squared times 2 is even. So on the right side, P squared must also be even, which means that P is even because P squared is even. So now we know that P is even. And if P is even, then P squared must be a multiple of 4 because if P has a factor of 2 in it, then P squared will have a factor of 4. And then if 2Q squared is a multiple of 4, then Q squared is even, and by the same logic as before, Q is also even. But now we have two even numbers that are in this fraction, which means it cannot be a fraction in simplest form. And them both being even means it can actually be simplified by dividing the top and bottom both by 2. So this contradiction proves that root 2 is irrational and cannot be written as a fraction in the form P over Q.
Proved by contrapositive. In logic, the contrapositive of a conditional statement is formed by negating both terms and reversing the direction of inference. Many important mathematical statements are the following form. If P is true, then Q is true. In a proof by contrapositive, instead of proving the original implication, you prove a different implication. Specifically, instead of proving the statement if P is true, then Q is true, we prove the statement if Q is false, then P is false. Statement 2 is called the contrapositive of statement 1. Next slide. This is a real-life example, original statement. If I had garbage bins closed properly, then the raccoons wouldn't have stolen my garbage. If the raccoons stole my garbage, then it didn't have garbage bins closed properly. This is the contrapositive. Next. Notation. Not P implies Q. It can be written as you can see it, and not P implies not Q. You can also see it. The contrapositive of P implies Q is not Q implies not P. This is a truth table, and according to this table, P implies Q and not Q implies not P are different ways of expressing the same thing. As you can see, their values aren't always the same in every row of the table. The expression not Q implies not P is called the contrapositive form of P implies Q. Next. Tautologies. So here you can see a list of statements. For example, A or B and C is equivalent to A or B and A or C. And this, for example, means that or distributes over and. And you can also see like De Morgan's laws. For example, not A or B is equal to not A and not B. So De Morgan's laws, the complement of the union of two sets is equal to the intersection of their individual complements, and the complement of the intersection of two sets is equal to the union of their individual complements. So many steps are proved by contrapositive. Write the original statement and indicate that you use proof by contrapositive to prove it. Then, 2. Write out the contrapositive of the statement that you're trying to prove, reducing the likelihood that you accidentally take the contrapositive incorrectly. 3. Prove the contrapositive of the statement using any proof technique that is most effective for proving this statement. So here you can see an outline. So proposition if P is in Q. So here's a back. Proof is then it's suppose not Q, and then we found out therefore not P. Next. A common mistake is to prove P implies Q by contrapositive, we should show that not Q implies not P. But however, it is incorrect to show that not P implies not Q. Showing that not P implies not Q proves that Q implies P and not the other way around. This is a very common mistake. Next slide. So here is an example. Suppose x is an integer of 7x plus 9 is even and x is odd. This is a direct rule. Suppose 7x plus 9 is even, then 7x plus 9 equals 2a for some integer a. We can subtract 6x plus 9 from both sides, and consequently, we can get x equals 2b plus 1, where b equals a minus 3x minus 5, which is an integer, so x is odd. A contrapositive proof is this. Suppose x is not odd. As x is even, x equals 2a for some integer a. Then 7x plus 9 is equal to 2 multiplied by 7a plus 4 in brackets plus 1. Therefore, 7x plus 9 equals 2b plus 1, where b is the integer 7a plus 4. Consequently, 7x plus 9 is odd, so 7x plus 9 is not even. Next. So, if x squared minus 6x plus 5 is even, then x is odd. A direct proof is not as simple as we should assume that x squared minus 6x plus 5 is even, so x squared minus 6x plus 5 equals 2a, and then transform it into x equals 2b plus 1 for b, where b is an integer. However, we have quadratic expression and a lot of steps are necessary. Try to solve the contrapositive proof for yourself. You have 3 minutes. So this is the contrapositive proof. Suppose x is not odd, so x is even, so x equals 2a for some integer a. So x squared minus 6x plus 5 is in the end equal to 2 multiplied by 2a squared minus 6a plus 2 plus 1. So we get x squared minus 6x plus 5 equals 2b plus 1, where b is the integer 2a squared minus 6a plus 2. Consequently, x squared minus 6x plus 5 is odd. Therefore, x squared minus 6x plus 5 is not even. Since x being not odd, so not Q, resulted in x squared minus 6x plus 5 being not even, not p. Then x squared minus 6x plus 5 being even, p, means that x is odd, q. So we have proved p implies q by proving not q implies not p.
Comparisons of both methods of proof. Contradiction. Assume for contradiction that not A is true. Use this assumption to prove contradiction. Contradiction proofs are often used when there is some binary choice between possibilities, for example, in number theory. They are not useful to prove formulas or equations, but sometimes can be used to prove their converse. Square root of 2 is either rational or irrational. There are infinitely many primes or there are finitely many primes. Either a line tangent to a circle is perpendicular to the radius of a circle containing the point of tangency or it is not. And the converse of the Pythagorean theorem also applies. Contrapositive. To prove A then B, prove its contrapositive statement, which is not B then not A. This approach is preferred if the contrapositive is easier to prove than the original conditional statement. Proving an or statement is tricky, but when we use contrapositive contraposition, we negate the or statement and turn it into an and.
Okay, so proving an or statement is tricky, but when we want to use contrapositive, we negate the or statement and turn it into an and statement to make the quadratic easier to understand. So for any integer a and b, a plus b is greater than 15 implies a is greater or equal to 15 or b is greater or equal to 15. By contrapositive, this means if a is less than 8 and b is less than 8, then a plus b is less than 15, which is easier to prove. So here are the proof by contrapositive versus proof by contradiction questions for the class. So which indirect method would you use to first prove the statement if 5x plus 25y equals 2019, then at least one of x and y is not an integer. So which would you use? So for the first one, if we're proving if 5x plus 25y equals 2019, then at least one of y and x is not an integer. So we would use contradiction. So if not p implies q contradicts, so we'd have 5x plus 25y equals 5 times x plus 5y. So 5x plus 25y is a multiple of 5. And since 5x plus 25y is equal to 2019, that says that 2019 is a multiple of 5, which is a contradiction. The second one is we're proving if mn is even, then either m is even or n is even. So this would be a we would use contrapositive. So our contrapositive statement would be p implies q is not q implies not p. So if both m and n are odd, then mn is odd. So let us assume that m and n are odd. Then there are whole numbers k and l, with m equals 2k plus 1 and n equals 2l plus 1. We have mn equals 2k plus 1 times 2l plus 1, so our two odd numbers. And we can expand that into 2kl plus 2k plus 2l plus 1 equals 2 times kl plus k plus l, because we factor out the 2 from each of it, plus 1. And since kl plus k plus l is a whole number, and then we're multiplying it by 2 to get an even number, and then when we add 1, we get an odd number, that means mn is odd, which means then we proved our contrapositive statement. And then the last one is prove the Pythagorean theorem with an indirect method. So we said this before, this is a contradiction, and this is part of the homework. And then here's an extra problem for the class that I will let you do.
Okay, so prove the arithmetic geometric mean equality by contradiction. That is, for two non-negative numbers a and b, half of a plus b is always equal to or greater than the square root of a multiplied by b. Next slide. So for two non-negative numbers a and b, the arithmetic geometric mean inequality is true, which states that half of a plus b is always equal to or greater than the square root of a multiplied by b. So let's assume the statement is false. Under this assumption, half of a plus b is less than the square root of a times b. Now we square both sides and get the quarter of a plus b squared is less than a times b. Multiply both sides by 4, and we get a plus b squared is less than 4ab. Now we expand the left-hand side and subtract 4ab from both sides in order to get a squared minus 2ab plus b squared is less than 0. And once we factor this, we realize that we have a minus b squared is less than 0, which is impossible because the square of any number is always positive or 0. So our original statement is true. Next slide. So second optional problem. Consider the following statement. If n squared is even, then n is even. Prove this through contrapositive. Next slide. So proof by contrapositive. If n is not even, then n squared is not even. Assume n is an odd integer. We can express n as n equals 2k plus 1, where 2k is an arbitrary integer. If n equals 2k plus 1, then n squared is equal to 2k plus 1 squared. And once we factor this out, we get n squared is equal to 4k squared plus 4k plus 1. And now we can factor the 2 out of 4k squared plus 4k in order to get n squared is equal to 2 multiplied by 2k squared plus 2k plus 1. And we can express 2k squared plus 2k as another integer, and we see it actually takes the original form as n equals 2k plus 1, making it an odd integer. So the right-hand side of the equation is odd. Thus, if n is odd, then n squared is odd. So if n squared is even, then n is even.
Here you can see the sources we used for our presentation. Thank you for your attention and participation. You can do the homework on indirect proofs that is in the chat.
This is Mathematical Induction by Timothy. Balint isn't here, and
me, Andy. So induction is a method of proof, and that's generally used for like a large set of elements with an arbitrary, or maybe with an arbitrary length, or it can be an infinitely large length. We're just trying to prove some maybe equation or some statement regarding these sets of numbers or the series. So essentially what happens is you basically prove a base case, and you prove that, and then the next thing you do is assume that if it works for the nth, then it works for the n plus 1. So you can think about it like a set of dominoes. If suppose I prove that I will hit the first one, and I prove that assuming one of them falls, the next one will fall, then I can show that if I hit the first one, then all of them will fall down. Now that's assuming the base case is the first one. Like if I prove that, if I say I'll hit like the one in the middle, and that's where my base case is, and I prove that if one falls, the next falls, then that will guaranteed work for everything past the base case. But any domino before that, not guaranteed to work. So it's usually good to start with the one at the very beginning. So in a dominoes, you can just hit the first one, and you prove that if one falls, the next falls, and that means all of them will fall since you started with the first one.
so these are the examples. So the first example is prove 3 to exponent of n minus 1 is a multiple of 2, where n is a whole number. So this is the solution. So we're going to start off with the first base case, which it's saying that n has to be a whole number, which means that our base case is going to be 0. And so we just plug in n equals 0, which gives us 1 minus 1 equals 0, which is true. And so now we're just going to assume n equals k. And we basically just sub in n for k. And we can assign a new variable a, and which is an integer. So we know that 2a is basically a multiple of 2. And we can move this minus 1 to the other side, which will be useful for later. And now our next case is going to be n equals k plus 1. And we just do the same thing. So we substitute n for k plus 1. So what we can do is we can use the exponent rule to bring this plus 1 out. So it'll be 3 to exponent k times 3 minus 1. And we can, there's this 3 to exponent k over here, and we could just bring this over. So we get 3 times 2a plus 1 minus 1. And we just distribute everything. And we can simplify it as well, which will give us 2 times 3a plus 1. And that basically means that since a is an integer, 2 times 3a plus 1 will always be a multiple of 2 because a is an integer. So here's our second example. It's a bit different. So we're going to prove that 1 plus 3 plus 5 plus so on and so forth plus 2n minus 1 is equal to 2 squared, where n is a natural number. So last time we used whole numbers, which had a base case of 0, but this time we're going to use natural numbers, which has a base case of 1. So we're going to test that. And 2n minus 1, 2 times 1 minus 1 is 1, and which is equal to 1 squared, which is also 1. And now we're just going to assume n equals k, same thing. So we're just going to assume that this statement is true. And we're going to test for n equals k plus 1, which is going to add a term at the end where n is k plus 1. So instead of 2n minus 1, it's 2 times k plus 1 minus 1. And then what we can do is we can take this entire section, which is 1 plus 5 plus so on, plus 2k minus 1, which is same thing as here, n equals k. And we can substitute that for k squared. And we can simplify this, the brackets. So it's 2k plus 2 minus 1, which is 2k just plus 1. So it will be k squared plus 2k plus 1. And you can refactor it to be k plus 1 squared. And this will work because basically if n equals k plus 1, then this k plus 1 squared is your answer.
So now we're going to look at a geometric proof. So the question is, show that any n by n grid, where n is the power of 2, where n is the power of 2, that it can be tiled by using only L-shaped tiles. Next slide. So just like an example, for example, if we're looking at a 4x4 grid, I can make any of tile I want just to be gone using just these L-shaped tiles. And you can see that I can do that for all bottom 4, and by symmetry I can do for all of those. So the question is, how can I prove that I can do this for any n by n grid where n is the power of 2? So let's look at a solution. So the base case is starting with just n equals to 2. And we can just see that I can tile I can just make any one I want disappear, and I can still tile it. Next slide. So now the method to show that assuming n is true, so assuming that I can put any one square I want disappeared, the question is, can I prove that the next power of 2 will work? So the strategy to do this is, if you look at the top right, if you look at the top right, I can essentially put since the next power of 2 will have you can essentially put all the corners right in the middle, and you can see this purple one was just showing that I can do that. And then you'll have an empty bottom square. And you can see that I put this red one to show that for a case of 2x2, the next one I can that one square there. And looking at the bottom left, I can rotate that red square any way I want, which would make any one square disappear. And I can essentially, since I can put any square I want to disappear for any n by n grid, I can just sort of stack 3 of them and have the ones that disappeared right together in the middle. So if you look at the bottom right one, you can see the purple one represents like the one that I could technically make disappear. And since there's 3 of them, I can just put one tile there. And then in the bottom right, you can see that I just filled the rest with a 4x4 grid, making one of them disappear. Essentially, the idea is that if I put all the ones disappear in the middle, then I fill that with a tile, then I can fill the remaining corner with anyone I want to disappear, and by symmetry, all 4 corners should still work. Next.
So this is another example, which is an algebraic example. So it is proof that 1 plus 1 over 2 times 1 plus 1 over 3, and so on, times 1 plus 1 over n is equal to n plus 1 over 2, is true for all integers greater than or equal to 2. So what would the base case be? Okay, so in this case, it would be 2, because we want basically the first one, which is the lowest number, and it would be 2 because it's greater or equal to 2. So I'm going to give you guys some time to try this question out. So maybe like 3 minutes, and then I'll come back and do the solution. Okay, so if you got a chance to look at it, I'm going to go through a solution right now. Okay, so as I said, the base case is n equals 2. So we just sub in 1 plus 1 over 2, which is 3 over 2. And we're going to do the same thing. We're going to assume that n equals k, which is, so we just replace n with k. And now we're just going to do this for k plus 1. And like the last example number 2, we're going to add an extra term at the end. And I just simplified here, so it's k plus 1 plus 1, and it'd be k plus 2. So now we're going to multiply like both sides by k plus 1. So we're going to multiply this original n equals k by both sides of 1 plus 1 over k plus 1. And then we're going to simplify this. So we're going to get k plus 1 over 2 times 1 plus 1 over k plus 1 is equal to k plus 1 over 2 times k plus 2 over k plus 1. And the k plus 1 cancel out, which gives us k plus 2 over 2. And you can see that this matches our test of n equals k plus 1. It's k plus 2 over 2. So that basically means that this is true. This is applications and variations. So we're going to talk about the historical applications. And so Plato's Parmenides may have contained the early examples of an implicit inductive proof, which basically means that it was not like directly written out, but it was kind of like implied. It was said, and using like logic, he figured it out. And the first rigorous use was by Gersonides in the 13th century, which was basically actually written out and directly expressed. And Pascal and Fermat also use induction in their proofs. So you can see that like induction has been like used for quite a while. And this is the variations. So strong induction assumes that the statement is true for all natural numbers and up to some value of n rather than just the previous number. So it's like only for like natural numbers, and there's also like a limit. And for different sets, different number sets or base cases, which we did, where n is not just equal to 0 or 1, it can be equal to 2, 3, it could be a negative number. So there's a lot of different ways that you could use induction.
So now we're going to look at one more geometry example, also with an algebraic example. So for any n by n grid of squares, show that the number of squares of all sizes within that grid is equal to the sum of the squares up to n. So like those square math questions asking you how many different squares in the shape. And then after that, prove that the sum of the squares up to n is equal to n times n plus 1 times 2n plus 1 over 6. So you can spend a few minutes to think about it. And if you don't want to do the geometric one first, you can kind of just start with the algebraic one. So it's up to you which one you want to do. Okay, it's been about 2 minutes. So I'll first start by taking up the geometric question. So next slide. So the first thing we're going to look at is, before looking at the proof, we're going to first notice that we can uniquely identify any square by its center and its size. So you can see there's a variety of different squares here. So some of the centers might be in the intersection of two lines on the grid, and some might just be within the middle of the square. Next slide. So we could start with a 2x2 base case, but we're gonna look at a 4x4 base case because since 2x2 won't be as easy to, is not as intuitive to how the rest of the proof works. So with the 4x4, we can see that if I want to find, well, if the number of 1x1 squares is 16, and you can see on the top left with all the blue ones, you can see that if it's a 1x1 square, it must start right in the center of them. And you can just see it forms like a square of possible squares. And then if you're looking at a 2x2 one, you can look at the top right image, and that one shows that the centers of them, which are in green, you can see that all 2x2 squares have to have a center of that, and each center can only have one 2x2 square corresponding to it. And again, that makes a sort of grid. And in the bottom left, you can see for a 3x3 grid, it's unique centers, which also makes a smaller square. And the bottom right, you can just see for a 4x4, it can only really have one unique center. So you can notice that for each size, it kind of creates like a square of possibilities, which kind of indicate that it will be a square. But just let's use induction to show that. The next slide. So the first three images on the top, you can see that for an n1 grid. So instead of putting every single possible center, I'm just going to use the corresponding colors for the different sizes. So there will be the same sizes and centers as before, just using those in the bottom for the corner. You can see if I increase the grid by, and increase it to n plus 1 by n plus 1, the center one will no longer be the center one because the center changes. However, you do gain 2 more at the bottom. And we can see that because each unique center and size creates like a square of possible squares, that will show that it does increase by another square of n plus 1. Because each time you add one, each time you add one, you remove the old center, but then you add 2 more. And also works for an odd case, as you can see in the bottom 3, in which the center happened to start on a like in the middle of a square. And this time I just added an orange circle because the previous one was just the 4x4. This one's 5x5. The next slide. So now the next part is proving that the sum of squares is equal to n times n plus 1 times 2n plus 1 over 6. The first step is prove the base case of n equals 1. Now, this wasn't the same one we used before, but this is just to show all of them. So we can just see 1 squared equals 1, and we can also see if I plug into the formula, I get also 1. So that works. Next slide. So now, assuming it's true for n, we're going to try to prove n plus 1. So on the left side, we just have the sum of squares all the way to n plus 1 squared. On the right side, we just have the formula we're trying to prove plus n plus 1 squared. So now we can manipulate the right side a bit. We're first going to factor in n plus 1 and then move the n plus 1 to a common denominator. So that's where we got the 6n plus 1 over 6. And then after that, we can just expand that numerator to 2n squared plus 7n plus 6. And then we can factor that for n plus 2 times 2n plus 3. And we already factored n plus 1 before, so we can just move it back up in the numerator. And now we can rewrite that as n plus 1 times n plus 1 plus 1 times 2n plus 1 plus 1, which is the same formula we had before. Instead of substituting n, it's substituting n plus 1. So we showed that it is true for n plus 1. So we proved the base case of n equals 1. We proved n plus 1, assuming n is true. Therefore, our induction proof is complete.
So these homework questions are in the PDF, which you'll get at the end. And these are our works cited. And thank you for listening to our presentation.